to talk to you guys about painting today. I did not paint this. I was going to joke that this is mostly what I'd spent my time on. Yeah, I'm Sam. I'm from Twitter. Work with Marius and thousands of other people who can claim the same spot. I want to talk to you today about a library called Hummingbird that we released to open source in September that we've been working on for about a year, and I would say really pulls together my thoughts and some of the evolving Twitter infrastructure thoughts on how to do streaming MapReduce at the scale that we have at Twitter, which is pretty staggering and makes me sad sometimes. So Hummingbird, open source. This is September 3rd. We've been promising it for a long time. Very happy to say it's finally out. We've got a bunch of internal systems on it, some of which we'll talk about today. And this is the work primarily of myself, Oscar Boykin, and then we did a lot of the early development of this. Later, this guy, Ashu Singhal, came on board, this amazing young guy from MIT. He really pushed out some of the first production apps and got this thing rolling internally. We've been running this stuff in production for about 9 months now at Twitter. Anyway. Okay, so what are we going to talk about today? We're going to talk about, can I carry this thing around? Not really. Okay, totally fine. So we're going to talk about what Hummingbird is, like what we built, what the vision for this thing is, and kind of why we thought that Twitter and the world needed yet another MapReduce library. These things are all over the place. I'm going to make the case that we needed one more to rule them all, but we'll see what you guys think. We're going to talk about what this thing can do today, some of the, the functions that it has, what we can build. And we're going to talk about how the design of Hummingbird enables you to build these batch real-time kind of Hadoop plus a system like Storm models. It's kind of an interesting way of building systems that the design of Hummingbird enables. We're going to talk about some currently deployed systems at Twitter, and then kind of what's next for the library. Okay, so vision. So why do we build Hummingbird? Twitter is a huge Hadoop shop. We'll go over, we have a number of clusters that are kind of 1,000+ nodes. We've got a ton of application logic and jobs running on Hadoop, baked into the Hadoop infrastructure. A lot of the data we generate is done as sort of key value processing by Hadoop. We wanted to start experimenting with Realtime, but it was just too big of a project to go completely switch over to new paradigms. We wanted a way to have users, when they use Hummingbird, write logic one time and have it run on Hadoop or on a real-time processing system like Storm, or potentially Akka, or potentially, Tage, or one of these other systems that are out there. We didn't want people to have to make systems decisions at the beginning of their experimentation with data. It's hard to go share logic. We wanted to try to fix that problem. Some context, this is like bragging about Twitter scale. We have a shit ton of tweets, we have a shit ton of nodes, we have a shit ton of users. Anyway, what this really means is like I worry about serialization problems a lot, and I don't want anyone else to have to do that. We want to solve these things. We want to solve systems problems one time. Ideally, our infrastructure team will impose some constraints on people who are building logic, as minimal as possible, and then we can go build optimizations on this more general idea of logic and let people go plug in their logic later. All these serialization issues that come with scale, all these message passing things. We want people to be able to build real-time systems and solve those issues without having to redo it every single time. Finally, we wanted to make non-trivial streaming MapReduce work in real time as easily as it does in Hadoop. So I guess the story of MapReduce at Twitter and at a lot of companies that do this stuff is, you're cooking along, you're doing complex, like unique counting, building models in Hadoop, all these things. You go to jump to a real-time model or some sort of model that computes in both systems, and it's kind of hard to figure out how to do like an exponential moving average in both systems and merge them, things like this. So what we found is that people would just sort of devolve to eventually doing like time series counts. It's easy to think about. Trivial MapReduce works, in these various systems, but harder stuff people were avoiding. So we wanted to make, unique set counts, model building, countman sketches, a lot of these approximate data techniques, as easy in the real-time world as it is in the Hadoop world. Again, logic one time, executing in both systems. So what did we build? what we came up with is we wrote it in Scala. It's a declarative MapReduce library that lets you build up what looks like Scala collection transformations. You're sort of doing your standard filter, flat map for each, these sorts of things. Really nothing's happening. You're building up a declarative data structure that describes a computation. Summingbird also comes with a number of platforms that can take that data structure and execute them with whatever systems sort of tweaking or decisions need to happen for, say, Storm or for Hadoop. And finally, this library introduces a few constraints that let us do very interesting things, such as running the same job on Hadoop and on Storm, and having a client that can go fetch and merge between those two things. So we're going to talk about how that's done. This is some kind of Summingbird code that, I guess it's pseudocode that I've written up, but this is basically what the library looks like. You've got sources of data that you're, flat mapping and filtering and merging together and doing all sorts of things to, at the end of the day, summing into a store. We'll talk a little more about how that works. But I guess the idea is most of this is applications pulling in functions from packages and applying them. Then you're handing them off at the bottom to a Scalding or a Storm system. I'm going to give a quick overview. Who here has coded Hadoop or done MapReduce stuff? Marius? Got it? Okay, good. Okay, so you guys kind of know the model. I figure the way this breaks down is some of you guys are hardened Hadoop experts, this is all you do all day. Some of you guys are just coming into this, haven't seen it before. So the quick overview of MapReduce, how these streams work, and specifically what I mean by streaming MapReduce versus MapReduce is a model that looks like this. So we have, in this picture, streams of events coming in. These might be tweets, impressions on our ads, things like that. We're going to perform some sort of flat map operation on those things. So these are transformations of the streams. A flat map would be a way to take one element in a set and convert it to 0 or more elements. You might be building, in this case, key value pairs out of, if you're looking at tweets and you want to build URL counts, pull a URL out, the key value pair is a URL and 1. You pass those along to these reducers, and what a streaming MapReduce system will do is, as each key value pair comes through, it will assign, for a particular key, all the values will go into one reduce function. So I have a plus here because, as we'll talk about in a minute, one of the big concepts that Summingbird really, really embraced that lets us do a ton of our systems optimizations and the batch real-time thing and all that is this idea of associative plus operations, the idea of the monoid. And I'm going to sell you guys on the monoid by the end of this talk. That's what you're going to walk away with, just a deep love for the monoid. And then you write out to some sort of storage layer. And the idea is that, by building this logic, whatever storage backend you use can reason about what the data is inside without sort of knowing how the data was generated. Your client should not care whether you took this picture and ran it on Storm or whether you took this picture and ran it on Hadoop. And to do that, we have to say, streaming MapReduce, the flow you build can kind of imagine that if one event came through at a time, that this would work. Anyway. So flat map, you can, if you have your flat map, you can build map and filter out of it. As I said, you transform each item in the stream to 0 or more things. Map is just emit a list of one thing. If you want to filter, just if the predicate passes, emit the one thing, otherwise cut it out of the stream. So you can do any general stream processing. Quick thing before we go into the monoids. I can't wait to get into the monoids. 4 concepts quickly. The idea was to build streaming MapReduce flows, 1, in a way where we could share logic, 2, in a way that you could build huge graphs of data on top of this thing. So when I write a Summingbird job that outputs some key value pair into a data store, I'd like that store to be available as a client to anybody at Twitter. Any service should be able to jack into that. And if I write my data out as I'm processing it, I should be able to sync it into some stream that their job should be able to consume as a data source. So you can imagine the sort of vast data graph that Twitter has. Right now, a lot of our jobs will just sort of look at the base streams that are coming in, the Twitter fire hose, the social hose, things like that. What we want is every layer of Summingbird jobs to be sort of a valid higher order data source in this level. Maybe that hasn't even run yet. Maybe that is just sort of a potential data source where if someone tries to subscribe to it, then the lower level stuff will get run. So the 4 concepts, quick overview of that we had to, that a platform that wants to run a Summingbird job has to define. We try to keep it small, are the like a data source, which is kind of a representation of like a stream in that particular system. In Storm, it's like a real-time queue. In Hadoop, it's like a set of folders that came from some, set of timestamps. That's the source. Store would be like just a key value store that you're aggregating into. The sink is like, you can basically like dump off as you're processing items just to another queue, and then the service lets you do key value lookup. So we're looking at this and we're like, once we got to this picture, like we fucking knew we were onto something, because as you guys can see here, every one of these concepts starts with so everything shares something in common. It's amazing. These are the 4 S's of Hummingbird. We're going to focus in on this S, which is the store. This is the real problem that I think was limiting my MapReduce jobs I was writing at Twitter. This is my issue. You go to write these jobs, you do the map and the reduce, you get the model. Then the question is like, what kinds of aggregations can you do? Is there if we want to be able to share logic but solve systems issues once, we need to place some constraints on the system. So what constraints can you place on a MapReduce job such that any value you emit, if it follows these constraints, I can handle it? What value thing? Turns out there's this amazing concept called the monoid. I was just talking to Tony about this earlier. It's like a freaky concept for people. I want to make the case here that just because it sounds like monad doesn't mean it's as scary. It's super easy. What we have here is, Java interface, closure protocol, Scala trait, whatever, with one method called plus. And this is just an associative operation. If you can take 2 of some particular type of value, smash them together into 1, and kick it out, you've got a monoid. It's amazing. The only other thing is this idea of a 0. So numbers have a monoid. You just add them. And a lot of these MapReduce jobs, like word count, will just use plus. But there's more complex data structures like sets have a monoid. You can just concatenate them or union them. The 0 is just the empty set in that case. No problem. Lists, concatenate. These are all the easy ones. Maps have a monoid. You just sort of recursively pull in a monoid on the value, and if you have a collision, use that monoid to smash things together. So super simple idea. Like I said, it turns out a bunch of structures have monoids that are more complicated than these basic ones we talked about. The hyperlog log is sort of an approximate like set counting data structure, super badass. It's got a monoid on it. The countmin sketch, Bloom filter, top K, like all these amazing things. And so what this means is when you're going to build analytics and MapReduce, all you need to do is find a data structure with a monoid on it, and it can go play in the streaming MapReduce world. So this seemed like a huge breakthrough. This seemed like, put this constraint in Hummingbird, and everyone's good to go. We wrote a library, or we released a library called Algebird that has a ton of these data structures and monoids in them. Totally awesome. Dude, tell me. The name? Algebra, yeah, it's got to have a bird name or it does not get out the door. There's a lot of cool shit internally that we're still spinning on. I know, it's many, many letters before. You could tell it was early in the process, I guess. Yeah, so we were stoked. Oscar and I were running around the office, like telling people like about monoids, trying to sell them. I felt like this, it was amazing. This is a conference on commercial uses of functional programming. So we did spread the word. We started out looking like this. I don't know if this is more of the reaction we would get when we would tell people. It was a little disheartening at first, but we built some cool shit and people came around. Anyway, functional programming, amazing things. Some of the words we choose are still frightening to people, and I haven't quite cracked that issue yet. So associativity. The monoid is amazing because associativity gives you huge abilities to perform systems optimizations. If you know your values that you're reducing, are associative, you can go ahead and parallelize many of the combinations on them. So if you go linearly add a bunch of things or perform some binary operation, 8 structures, takes 7 steps, it's linear, fires up again and processes forward, it's going to go ahead and knock out that error. That batch, as we move forward, is now served by Hadoop. So we've got the system that at the client level looks like it's being run by one sort of self-correcting, eventually consistent store. Behind the scenes, you're delegating out to various backing stores, or backing like processing systems. The current one is just Hadoop plus Storm, but there are some more interesting ones you can imagine. As it gets easier and easier to kind of merge things together, you can imagine initial sort of ETL pipelines running in Hadoop, and then you delegate out to some iterative, Spark processing, and then jump out to real-time for alerts. And there's a monad here, is what I'm trying to say. Like, you should be able to flat map to other platforms. But anyway, so we went through all that. Okay. What's a product we built on this? We've done a lot of stuff internally. One that just came out recently that I like, it's simple to think about the logic, is this feature of what we wanted to build, and what an intern actually ended up building was tweets get embedded all over the web. So when a tweet gets embedded, it shows up in the site, and we get sort of a stream of impressions that happen on those things. If you look at a tweet, it would be nice to get backlinks to those pages that have embedded a tweet to see a little context around what's going on. Turns out, trivial thing to do in Hummingbird, and we built just a product that does this. I'm going to show you the code that makes it happen. So you go to a tweet, you can click embed, and place this thing on a website. So this is, basically a story about this feature. Whenever users look at this, when you visit the tweet and expand it out, you get this list of related headlines that have gone ahead and embedded this tweet. So this is updated in real time, like within a second or so. If you embed a tweet and people start looking at it, it's going to show up in the tweet expand, super fast. The MapReduce diagram for that, again, like all we're doing here is thinking about the key value pairs. Every time you see an impression coming off of this queue, go ahead and pull out the tweet ID that was looked at, and what you emit is your key value pairs is a pair of tweet ID. The value is a map of URL to count. Again, maps have a monoid. We can go ahead and just, add these things together. Anytime there's a clash in the count, add them up. So accumulating in the data store for every tweet ID is this map of who's embedded and a count of how many times that was viewed. So no problem. This is what the actual job looks like. It's long because they're doing something a little more complicated. Basically, like often the popular tweets will get embedded in a ton of different websites. You'll have an enormous map. These guys are actually using an approximate data structure called a countmin sketch to sort of process. So, to be honest, a lot of the jank here is converting from, and there's like Java to Scala safe, like making sure that we don't get nulls. So anyway, this is the job. You can see we take a source in, we filter out events, we're generating two types of key value pairs. All of this is logic of the job, except for the null handling. And then we go ahead and we say sum into the store. The default monoid, the type system can figure out the value is a map of URL to long. Go ahead and sort of suck in out of Scala implicit compiler land the right monoid. Boom, good to go. So anyway, they do something a little more complicated, but we don't need to go into that. What else have we built on this? Publicly, the big one is we have this advertising center with a bunch of advertiser dashboards that are essentially these like complex time series of unique visitors, counts, all sorts of aggregations. All of that is backed by Hummingbird. It's trivial to go extend this product to new data structures because what do? We want to go do a top K aggregation. Again, this unique thing, no problem. Just drop in a slightly more complex value and the monoid will sort of take care of it. And then do a shit ton of UI code to, and HTML and JavaScript to make it look nice. But that's where the effort goes instead of these backend systems things. So that's what we built. What's next? What are we going to do? Future plans are, and again, this is open source, but future plans are to extend this to different execution platforms. We want to go write backends for the platforms you guys might be running. We've got an in-memory one. The idea is that, again, like you should be able to publish and share logic and tutorials and snippets online and have anybody be able to try them out on their architecture with their backing stores, no problem. More pluggable graph optimizations. The various planners do different sort of filter push down into their sources, things like that. We want to have more sort of pluggable ones of those. Metadata publishing, building these huge data graphs is interesting. And practically, like in the open source world, just more support for AWS and EC2 tooling so that people can just pick this stuff up and use it right out of the box. And more tutorials. It's open source. You can kind of see we do all of our work on GitHub. So if you're curious and you want to contribute or check out kind of where this is going next, or just see like engineers who've been working together closely for years, like fighting and being sort of snippy to each other, come check out the discussion on the GitHub issues. Yeah, so quick summary. The takeaway point is that this system with its various constraints and this monoid thing turns out to be appropriate for the majority of real-time apps that we have running at Twitter now that have started to use Storm. I think about half the jobs on our Storm cluster have started to use this stuff. It turns out to just be easier to reason about. And you can go ahead and take your real-time job that you want to run, do various load testing and capacity testing on Hadoop. It's really, really nice to be able to not commit to a system and have to bake your sort of design decisions in. All about the monoid, especially if you're like working in untyped languages and you're a little nervous about like whether this will work. It does. I've done a lot of the stuff in Clojure. It's badass, except the constraints. Yeah, data scientists who aren't familiar with this stuff can deploy real-time systems. Not to like rag on data scientists, but it's really nice to not have to sort of worry that you're getting into a mire of systems decisions. And, you know, we can reuse a lot of code. And yeah, anyway, that's what I got. Anytime.
So how much of the ecosystem impact does this framework? I mean, did you have to make changes to the framework to get ecosystem?
Sorry, the Hadoop which framework? Oh, so we didn't really. We were riding on top of this. The question was, did the system have to sort of change it all to accommodate Hadoop's MapReduce framework? And we ride on this library called Scalding that we've also developed, which at the end of the day looks kind of like Summingbird, which takes care of a lot of the optimizations we needed. We didn't really have to change much. Hadoop is kind of like the archetypal key value system. Of course, there's sort of issues with configuring Hadoop properly and all that, but at the end of the day, like, we didn't really have to make any sacrifices for Hadoop. The bigger sacrifices are sort of figuring out what operations can work, potentially for real time, potentially for Hadoop, and only letting operations into our data graph that can handle both those cases.
So you mentioned just briefly the monoid, right?
Monoid or monad?
Monoid.
Okay. Okay.
So I noticed you're only assuming associativity.
Yep.
Often when it's kind of trick, when also like the community there, I noticed there's like at the bottom
You saw it.
little thing where you, so like it sounds like so. One is, are there any good examples of important non-commutative mergers?
Yep.
Operators? And the other is, what do you do differently with your solution?
Okay, good questions. The question is, how do you got to like, we like associativity, what about commutativity? That should just be baked into Algebird, that a monoid can be marked as commutative. We've been kind of fighting about the right way to do that. When we know something is commutative, we can do more optimizations like map site aggregation using the same monoid. We can go ahead and sort of, that helps with data skew a lot. It's huge. We can sort of pepper these pre-aggregations all over the system. An example of an important non-commutative operation or application would be, I think, Twitter itself. Like if you wanted to build, right? You want to build the Twitter, basically like the list monoid. When you want to build like the Twitter timeline on the thing, you can imagine that as the key would be like user ID, comma, some time bucket, and then the value is a list of tweets that showed up in your timeline for that time bucket. So ordering does really matter there. And when we start doing, if we started doing pre-aggregations and sort of having people bunch up their lists and then concatenating those, we're going to get this non-deterministic order that we can't work with. But yeah, associativity is big. Commutativity is like even better. And